gets your serial number, and then opens a stream to this domain. And then since it's actually running on a computer and I don't have text message functionality, I just put generic text message hard-coded whenever message body is called. So they're essentially sending out your text, the message. I'm not sure what this string is, but this is the number that I've hard-coded for your phone number. So it'll essentially send any text message you have to this website with your number and the message. So we ran this tool on various applications, and there's a major carriers application which had a hard-coded key. And so just looking through the files, you can see the byte representation and the string representation of the key. So obviously a hard-coded key isn't good, and they also used a hard-coded IV, and essentially the IV is all zeros, and then you can see the key $, etc. So in this way, I mean, if you hard code a key in an application, somebody can just disassemble it and then get the key value and then decrypt any traffic you send from that. So that's obviously not recommended. And there's also the other application after this one uses a fairly predictable way to generate the keys, which is also fairly insecure, as I'll show. So seeing the, looking into the Smalley files where the key is generated shows that they actually just use that string, get the bytes, and set that as a static variable called key value. And in some of these files, I've tried to redact the name of the application just because I'm not supposed to say it. If I say it, I don't mean to. It's just my mind's pretty closely associated with it, looking at this stuff. And then so there's also the IV value. If you look in there, it's essentially just a hard-coded byte array that they use. So once I had that key, I wanted to see exactly what it was used for. So I looked into the shared preferences file and saw saved password. It looks like something in base 64. I tried to decrypt that. I couldn't. The decryption wouldn't actually go through. So just used, it was an AES key. So just initialize the key, the IV value, decode it from base 64, trying to decrypt it. Didn't work. So I identified where it's reachable from, or at least the activity that uses the hard-coded credentials. Essentially, this is kind of my reasoning, or going through and trying to find exactly the path to reach that point, so I could exercise the code to see if that was actually being used, because I found that in the forced execution emulator, so I don't know if that is actually reachable when you run it on a real device. So I repackaged it, disassembled it, added data into the application to show that it was reaching certain points, and just writing that to the log so I could see as I was executing it where exactly I was reaching. And also, obviously, application repackaging can be pretty bad because it looks like the same app, but it could just be leaking your credentials or stealing data and sending it out, exfiltration. Here's more about rogue apps. Yeah, so there's a few different attacks they could try and do. And I mean, it'll obviously look like the real app. I mean, you could tell because it would be signed by a different key. And there's other methods to try and determine whether the application is repackaged or not. And to glean some more information from the code, exactly what was going on, they had a logger class, which throughout the application code, they would write things to the log. But actually, in their own logger class, it seemed like they had written to the Android OS log, but they removed that since it's actually production code now. So essentially what I did was I put back in writing to the log so I could get various debug messages as the application was executing. And here's kind of an example. So for their log file, this is Smalley again. So there's a pretty well-defined process for instrumenting it. So I write my own tag to the log so it's easy to identify, and then the parameter string, and then essentially you just recompile the application, sign it, and then align it and install it to a phone. And so after I did that, I noticed that they were writing the wireless number and the password to the log. So I redacted that, and I also changed the number. But you can get a fair amount of information just by activating the debug code, which a lot of apps seem to have that in there. And sometimes it's easy as there will be a Boolean in a certain file, and they'll be checking that before they write to the log. So you can just set that as true and then turn on the debug code again, which is fairly easy. So in production code, you should definitely remove the logging because that makes it a lot easier, especially if it's obfuscated. This app wasn't obfuscated, but if it was, it would have been a lot more difficult. It's actually, if you are an app developer, it would be good to run ProGuard and obfuscate your code so your class names and method names don't have meaningful values. It's just AA, AB, something that you can't really glean any information from. So I saw that it was in the update password activity. So after instrumenting it, I wanted to see if I could reach the hard-coded key to see exactly what they would decrypt, because it was some sort of decryption routine to see what they were doing with the hard-coded key. So there's the application, a screenshot, and then actually going through the update password activity, it would not let me do it, at least for mobile. So, and once it returned that message from the server, it wouldn't enter the branch to actually do the decryption. So I got to the method of it, but I couldn't actually get there. So I think they were possibly aware of it and deactivated that functionality at the server level so that you couldn't actually exercise that code in the application. And then I also tried it again, but it was giving me some sort of error. And this was going on for 2 weeks when I was trying it, and then I kind of just gave up. But we told them about it, and I would assume they fixed it. I'm not sure. So since they disabled that at the server side, I wasn't actually able to exercise that code. So the next app is it's a financial application, and essentially it's an account aggregator. And they make a claim on their website that if you lose your phone, that you won't be able to, nobody will be able to access your data. And if you can get past the screen lock, you can do that. And if you have USB debugging on your phone enabled, then you can get past the screen lock. And there was an encrypted database, and then also they use shared preferences, and anytime before they would write to shared preferences, they would encrypt the value, and then when retrieving it, they would decrypt it. And I was essentially able to get everything on the phone. So you can see all the transactions. They have certain account details, and in one instance, there were 2 of my credit card numbers in this database. And that was kind of in a particular scenario where I had a transfer from one credit card to another because I closed one out and had a negative balance, so it got transferred to another credit card. So in that, it exposed both my credit card numbers. And so to kind of reverse this, or to look at it or obtain information, I started to instrument it to get certain values to help me kind of find out what's going on. So here's a screenshot of it, and I see in the encrypted database they have your balance and cash flow So I went into the database and I changed the values to negative a billion. And so shared preferences is essentially per app, persistent storage, writes the values, it's key value pairs, it writes in an XML file. And it encodes the key values and then or using some random double value. And it seems like looking for the key, it doesn't seem like they're stored anywhere on the application, but they're generated using a fairly predictable routine at runtime. So here's a printout of the shared preferences file. So you can see, well, I guess they are, the key values are also encrypted as well, but when you decrypt them, it's the weird double value. So you can see the value, or the value, when it's decrypted, it's, you don't actually see the name. There's like a transformation process there. So here's how they generated the key. So it was the first 8 bytes of the device ID, then the device, next 7 bytes of device ID, manufacturer, model, and then a hard-coded string. And then they would just take the first 32 bytes of that and use that is an AES key. And then on our text phone, or test phone, the value shown below what it, when we were running it. So based on that, created a routine to decrypt it. So you just create the key. And
Do we all understand what the problem is with this? That someone else who doesn't know your device can generate basically the key that they're using to encrypt it. Because this type of device information is available to an attacker. So basically the encryption that they use is useless because the key is actually automatically predictably automatic.
yeah, because you can essentially use API calls to obtain all this information. So if you run code on that phone, you can obtain all these values and then create the key. So decrypting the shared preferences file, you can see the double values, but then I instrumented before they did the transformation to show what they actually correspond to. So there's a login token, so you could take that and essentially log in from a different phone. And then the passcode is the PIN. So generally the application is protected by a PIN. So you can obtain the PIN and then you can get into the application and look at anything you want. There's the cookie. And just some user ID values. So also going through the applications file, there's an encrypted database since they say so. But if you hex dump it, you can see that it's encrypted. So this database has all sorts of stuff like transactions, bank account information. And I was looking to see if they store your bank credentials. That's one of the things I was going for. And in one of the databases, they actually do have a column for it, but they don't actually use it, or at least not in the version of the application that I had. So looking through the code to see, looking through the Smalley code, you can see how they generate the key for the database. Again, there's device ID, creation date, and hard-coded string. So there's the call. It shows how to get the device ID. And then you can look in the timestamp file to get that value. And in the string table, there's a field called do not mess with me. And you essentially go in the string table and find it, concatenate them all together. I believe the first 32 bytes are the key. So here's kind of just a routine to generate the key. And then once you have the key, I believe it encrypts that same string, that hard-coded value, and the result of that encryption is the key. So it's all fairly predictable. So, and they also use a third-party library called SQL Cipher API. So I essentially just looked at the application code to see how they were using it and did it myself. and also looked at the documentation for the SQL Cipher API, and then just looked to see what tables there were, and then just iterated through all the tables. They also have a SQL file that has the table definition of everything. So going through, there were only a couple interesting tables. Account. So there's some bank account info. I didn't find the credentials there. There's a transaction, so you can see where you spent money, how much you spent money. And the login table, which didn't have the credentials either. And you can kind of see below the SQL statement for creating the login table. And another thing to help me figure out what was going on, they rely, before they write on the log, they use a call. I believe it's log.isLoggable, and you provide the tag and then a certain level. And using ADB, you can set properties so that I looked through the code, see exactly where they were calling that, and then got the actual tag values, and then I essentially just set them all to verbose. So as you run the application, it will dump all the SQL statements it's running, and actually quite a few other things that. So essentially just instrumented the app, and then also set the debug tags to get more information to see exactly what was going on. So with this, you can see, and also you can see the network traffic as well when you set the tags or set properties for the certain tags they're using for the network traffic. And so for all of them, you can see the last 4 digits of the credit card number account, which isn't really that big of a deal. But in that specific instance, I did see my credit card numbers, which was obviously bad. And so some of the developers do make mistakes, even unintentionally. Maybe they store PII on the SD card, which is readable by any application on the phone, or maybe they make network calls out not over SSL or not encrypted. And let me just open the log real quick for Mint, or so let's see. So just instrumenting it, and then also setting the debug code. Here's essentially the Android log, and you can see the tags and then the values written to it. So you just instrument certain points, so as it's running, you can essentially just instrument code to dump the password that it's using. Also how they're generating the key, or the key value. And in this instrumenting it, I was able to have it dump the bank credentials. So like putting this on I've redacted part of it. So I mean, here would be part of my username and part of my password. So if you put this app out there, instead of just writing it to the log, you could send it over a socket to some remote server. And you can see some of the, and for the credit card number, I've redacted it, but so this essentially was a transfer from one card to another. So, and in that instance, it had the credit card details, or the number from this credit card and the credit card it was transferred from in the log. I'm not sure if it actually shows up in the app, but then you can also see all the transactions in here. So, and like how much money, so this would be something like that at a gas station. And it's actually a really large file, so just running the app for a little while, instrumenting it, reactivating the logging. And certainly get a lot of, you can see all the things it's doing to the database. You can see the token going out. And also instrument it to dump the bank credentials as well. So to wrap it up, kind of going back to some of the earlier tools, when you are an Android application developer, you don't want to have it over-permissioned or under-permissioned because it may crash. Over-permissioned, it may prevent some people from actually installing it because it has maybe permissions that it doesn't use, but permissions that are scary enough to prevent somebody from using it. And obviously you don't want to use hard-coded keys. Somebody can essentially just look into the application code and dump that. And you don't want predictable keys either. I mean, you want something with some entropy. And another good thing if you are an application developer is to obfuscate your code to make reversing it harder. You can do that using ProGuard. It's not that difficult. And when you're within an application, when you're communicating with other application components, you want to use explicit intents. And you also want to make sure that other applications can't launch your application components from another application. And you just do that through explicit intents and then not export your application components or use custom permissions. And you definitely want to remove the logging. A lot of people seem to leave that in there, at least on production code. It certainly makes it a lot easier to see what's going on within the application because some of these applications are fairly large. And that will dump a lot of the values to the log. And you kind of can see some of the state of some of the variables and exactly what's going on and what you're triggering. And obviously, application repackaging is an issue. It happens quite a bit. Somebody can take whatever application you have, put in code to dump anything they want or do anything they want. It will look like your application, and they can steal your information, intercept it, do whatever they want with it, and you might not know. So, I mean, there's ways to tell that something's instrumented, but I'm not going to get into that here. Questions?
We will be moving on to the next session, which is a bit more about coding. Paul is going to give you a presentation, as we said, about multi-threading. With the permitting time, I might be able to talk a little bit about power analysis, and we will wrap up this tutorial. But I will make sure that you get we have a lot of slides, so if you want to get them electronically, I'm going to have to give you the PDF. If you want to get them printed, you can email me and we can print out a version for you. But there are a lot of them, so the electronic version seems more reasonable. In this one, we will have more actual code on the phone. So he will going to give you tips now that are a bit different from the actual tools. You don't have to. I have mine. It's okay.
No, the connectors are different.
Okay. So without further ado, Rahul is going to be talking. Let's start the presentation. You need to connect this guy. Need to turn it around. Yep. And then we put it, just pull it up. You have to mirror the displays. Or actually, you know what, if you, no, you don't have to.
I want to because I want to see the same. Oh, you're saying that they do it?
Probably, yes. You will be able to see the presentation. Just that.
This is good. Yeah. All right. So I'm going to. My name is Rahul Murmuria, and I'm going to speak about multi-threading in JNI, and more specifically certain reliability and security issues that come up while writing multi-threaded programming. A lot of you might have done Android programming, in which case you would have come across either one of these two, but I'll focus on a general knowledge level. So multi-core processors weren't common in Android phones in the beginning until Android version 1.6. There were no multi-processor devices, and therefore Android was not capable of handling multi-threaded programs. What they did was Dalvik was a single instance, and multi-thread. If you did multi-threaded programming, they were just time shared. But recently, once Honeycomb and the new Jelly Bean versions of Android has come out, multi-threading has become really efficient on Android OS, and we can use multi-core features for various things, like if you have a user interface and you have network communication, it is of course good coding practice to write two separate threads, one dealing with the network, one with the user interface. But also now, because there's multi-core processors, you can assign each thread to a different core, right? So concurrency is definitely a plus on Android now, and there is no downside to it. If you have code that can be parallelized, then it is definitely a must that you should go with. You should think about threading from the ground up, right? So what do we lose if we write multi-threaded programs? There are a lot of complaints from programmers about bugs that arise when you have deadlocks and all other issues with multi-threading, which are known from Linux days. And on Android, multi-threading has specialized APIs which give you very easy methods of implementing threads, and you don't really have to worry about deadlocks. Therefore, multi-threading does not always lead to bugs, and it is definitely worth looking into. And they are also not power inefficient, because if you have single threads running at running on full frequency, what happens is that you have overheating, and that consumes a lot of battery, and therefore multi-threaded programs do improve the battery life of your phone. There are the APIs you had for regular Java programs. They exist. The same classes exist on Android, but there is also additional APIs that Android has provided developers, and that goes both in Java space as well as C space. Why does Google need to do that? Because on Android, you don't write regular software. You have applications which have user interface. So all of them have an activity. All of them have a service running. So there is certain common features between applications, and therefore it makes sense to provide APIs that do certain known tasks in a standardized way. And therefore Google has created these APIs which help you do multi-threading in a very easy way. And the choice of what API you would use depends on what you're intending to do on the phone. For example, if you're working with the user interface and you need to make sure that it's responsive to a user, then you would use the API that is meant for the user interface. And there is a very easy way of specifying what code goes in the background and what runs either before the background processing is over or after the background processing is over. And we will look into a sample of that in the upcoming slides. The other reason why you would use multi-threading is, of course, speed and efficiency, which is what we have always used it for. And I mean, this would be done using the thread pools, but again, Android has given certain libraries that we can look into. And some of the use cases would be if you're loading multiple images and it's a scrollable list. So you don't want the UI thread to get stuck when you're scrolling the view. And so all the images are processed in the background thread. So these are specific Android libraries. You can think of this as additional use cases which are common. They don't cover all cases, but the things that these don't cover, you would use traditional Java threading for that. So we're diving a little bit more into the code. So this is an activity class, and if you don't know programming on Android, activities are the classes that are the screen that is the view which you see, the user interface. It's usually called an activity, and that is where you define whatever objects you have on the screen, text boxes, buttons. So this has to be available for I/O at all times, and therefore this onCreate method is the first method that is executed whenever an activity comes up. And if you look at the set context view, that is just the layout that is visible on the screen, and then what this application is intending to do is that after 10 seconds it should respond to the user saying, how are you? And there is a thread sleep in the middle. So what is wrong with this code?
After 5 seconds, the OS will be like, hey, this is unresponsive, you want to kill it?
Yes. So basically, this is the UI thread, and UI thread's supposed to be available, and if you make it sleep for 10 seconds, it either, if you're on one of the modern newer Android versions, it will give you a pop-up which says that do you want to kill it. If it is on an older Android, it will just crash. The app will just crash. So this is a complete not recommended code for Android. And how would you write this in a nicer way? So we are going to remove the burden of the sleep from the user interface, and the way to do that is, first of all, clean up the onCreate method. So onCreate has only the layout, and then what you do is that you create a class. You create a class that deals with the sleeping in the background, right? And I'll tell you what's so the view setter class is something that we have defined within our own application. There is, and this is what it looks like. So this extends async task. Now that is the multi-threading API for user interface that Android has designed. And the way this works is that you have a method do in background, and you have on post execute. So Android knows that whatever you put inside do in background, it will run in a separate thread, and while that happens, it will let the UI thread be available to the user, and you can add code in this which puts a spinner on the UI, or it can say please wait, or any kind of message, which I have not included here, but that is usually what applications do. Otherwise you'll just see activity that's just waiting, right? So then when you use the on post execute, you can specify the set text and the log. So set text and log, I have two statements which were also in the initial program, the badly written one, and the difference is that set text is a method called upon the text view, so that goes on the screen, and the log.v goes inside the logs, system logs. So the reason I put both the commands is that you can see, you can check if whether they execute before or after the sleep, and you'd notice that sometimes the log comes up in the logs pretty early. It doesn't wait for 10 seconds, and that is just instability of the code in this badly written code. Whereas here in the, once we removed the sleep from on create, we called this thread, we call this class in task.execute my text, and we are passing my text as an argument to the class. So when the class executes set text, it is getting my text from the original UI thread, and that happens using the first parameter that you see in async task, which is a string. So now the UI thread does not sleep. It is available for 10 seconds, and you get these two messages exactly after 10 seconds. So this is basically removing any. So if you have any code that is heavy, whether it is downloading a picture or prompting the user for some login prompt, all of the processing has to be done in a background thread like this, and the user interface UI thread has to be lightweight. It should do its job and not sleep ever. And if you do any kind of heavy processing, it's worse if the user presses on the screen, because in that case the user interface gets input and there is no CPU to actually process it, because the user interface thread is doing something in the background. So it's worse if the user is pressing on the screen. So it's important to keep the user interface up and give a spinner box or a timer saying that please wait. Yeah. So we can look at some memory analysis of the code, and I'm going to use an application which was by a person from Google. It was on the Android developer blog, and what we are going to do is we are going to analyze it using a memory analyzer. There's more than one tool for it, and so why do we need to do that? Why do we need to look into the memory? When you write any code, whether it is on Android or on any other OS, you need to look into the memory leaks. You need to look into weak references, and this can potentially crash the application, because because there's a limited heap size on for any given process, and if your application uses up all of the heap, then you get out of memory error and the application crashes. So it's important for us to make sure that our application is playing nice with the memory. And also on Android, just as any Linux, but on Android we have the physical RAM does not exactly map to the process, the RAM allotted to the process, because there is a lot of shared pages, and usually if you total up all the values that are given to you for memory consumption, it would end up being much larger than the actual RAM. So there is something called PSS value that you will see in the numbers that I'll show up now, and that is the right metric to use. And the way they calculate that is they take the physical, they take the active. So there's active and then there's shared memory, and the active memory is taken as it is, and then the shared memory is divided by the number of processes that are using that page at any given time. So it is you can say it's an approximate figure, because you really don't know how much of that page each process is using, but that is how Linux works, and that is how Android works. So we're going to look into some of this, and I have a phone here which has a couple of applications running on it. So let me show you. Okay. That's too big. Okay. So this is an application that I'm using right now, and this is something I wrote, and all it does is it has a background thread that is looping, doing nothing, and there are certain activities I have, like this one. It loads some OpenGL boxes and triangles, right? So what I'm going to do is look at now this is showing you the list of all processes and how much memory it's consuming, and it's sorted in order of PSS, which is the the ratio, which is the calculated memory consumption, and the one we spawned. So we need to use the meminfo, and yeah, here it is. This is the application that you just saw. And if we have to actually look into this application, we can copy this package name, which is the process name, and so we get to see, I mean, the views is 81, and then if you look at, so the views is growing because when I use the OpenGL, when I use the OpenGL icon, it changes the view, and then I go back and it changes the view again, and so you see this count increasing, and also you can see that the PSS column is here. It tells you how much the Dalvik is using, how much maybe there's a JNI involved, or so it's telling you each of the components how much it's using, and you can look at the total memory. The reason this is useful is that you can compare with other applications, and also you can, if you're not the developer, you're the user, you can check for attacks using this method. And there is also another tool that helps you look at memory leaks. So I'm going to show that next. So we have the process here, and that's actually the threads that is running right now. And if I start the logger thread, you can see that the value on top is increasing, and you have an extra process that came up here. Also, if we look at the memory dump, you can look at leak suspects. So what this is showing is whether there's a memory leak or not, and memory leak can happen if you have any so if you're referencing a object and the link to it gets destroyed but not the object, or if you have a buffer overflow, any of such issues, you can have a memory leak. Here what you're seeing is two suspects, and these both suspects are part of the UI. This is from the resources, this is from bitmap, and you can see that this was loaded by system class loader. So that's not our class which is loading it, this is higher up in the API. So this is probably one of the UI threads, and it's active, it doesn't die, so therefore the tool is reporting this as a memory leak, as a possible memory leak, but it's not. So we know that. What we are interested in is the remaining alerts, and there are none. So we can say that this tool thinks that the application is free of memory leaks. So this is some of the tools that we have for looking into the memory, and so this is called Memory Analyzer, and this is available for all Java programs, not just Android. Okay, and let's continue with the presentation. So as we saw, we can look into the memory, and we can find out for each process or each thread how much is being consumed. Oh, there's one more thing that you could see there, by the way. If you go into the memory analyzer's output, okay, I need to look at the interface, but it's supposed to show you how many calls were made to each thread. So if you have a thread that shows up like 3,000 calls, and then the other threads don't show any calls, that means that you have something wrong with your code. So that's one of the things that can be looked into using the memory analyzer tool. And yeah, so that was looking at the UI thread with a async task. The other type of threading is using a thread pool, and this is done when you have a lot of background processing and you want to multi-thread the data intensive task, and it's not something to do with the user interface. And for that, you would create something like a thread pool, which is so this is taken from a photo manager application, which is there on the developer website as a sample for sending jobs to multiple threads. And the way this uses this thread pool executor. So you can define how many threads, or you can say it's based on number of cores, and you can give it how much time. So this is not a one-time thread. Unlike the UI, you can keep reusing the threads and repeating it in a loop. So the code for this, the sample code for this is it's called threadsample.zip, and it's on developer website. And if we need to do thread pools, this is a very good sample to start from. And here's the link for that. And I'm not going to go in detail for thread pools because it's more or less the same as thread pools on Java. The async task was something unique to Android, but thread pools are not. And so let's go into discussing why we would need native code. So Android has Java applications. It also has, you can also write programs in native code, which is C, C++. And some of the reasons why you would want to use that is there is IOCTL calls if you want to explore certain CPU features, and write assembly code even maybe for using the instruction set of the CPU, or if you have any libraries that you want to support. For example, there was a, so when we were in the Android 1.6 time, there was no ad hoc Wi-Fi module on Android, and one of the things we could do was compile libipq, which is the deprecated precursor to netfilter for routing, and we were able to compile that library and use it on the phone. So if you have any legacy C programming libraries, you can support it using JNI, using native code. And then they also have OpenGL support in case you want to write user interface directly in C. And all of this is provided using Bionic C library. So it's not the glibc, or it's not any standard previously known C library. Android made their own C library, and so of course there is two ways of writing native code, right? One is you create your user UI in Java, and you create a native interface to call functions which are written in C. And you can also actually write pure native code with user interface code as well. So both options are available, and both options give you the same library. So the Bionic C library is used for whether you're creating functions which are called in Java or you're creating completely native code. So if you want to write a JNI application, I'll just briefly go through the steps. If you can create a project, suppose you created a project hello JNI. The Java code would be under the SRC folder, and we can create any other folder for the C native code, and you can call any name to your C programs, right? And this is what the JNI would look like. This is standard JNI. This is no change on Android as compared to the way you did it with Java. You have the JNI.h, which has the definitions for JNI env, and that is basically the environment variable which you see here. So that's passing the reason you have this is it stores it stores the local variables. So when you call this function from Java and you pass it arguments, the arguments are local, and they would be stored in the JNI env. And if you have multiple calls made to the JNI function, or if you have multi-threading inside the function, it doesn't have global variables. All the variables. So for each instance of the JNI call, you'll have a separate JNI env. So the environment variable is specific to each call, and therefore you have local variables. There is a way to define global variables, which we'll look at later. And there is also the other thing you need to notice is there is a format in which the functions are named, and the naming has a logic. The reason it's named like this is because this is your package name of the application, edu gmu hello JNI, and that is followed by the activity name that made the call to this function from Java, and then the function name. And in the Java space, you will have the same function name. So you'll call it by string from JNI. That will be the function name in Java space. So and as you can see, this is returning a string. So you can make this call from Java and use it like any other function. The way to compile a JNI program is different from Java. You have to use you have to create a makefile, a build file basically, and this is similar to make, but it is this is using the Ant and Apache Ant if you've used build systems other than make. I mean, this is pretty standard. You can give this is local path means just that you're talking to the current, looking into the current directory, and you're going to save the previous includes, because you need to specify whether you're building a shared library or an executable or a static library, and that's done using the include variable. And then you just specify the name of your binary and the name, and list all your source files here. So it's a pretty straightforward build file. It's called android.mk, and it is required to make this android.mk along with your C files, and it needs to be compiled, and you can compile it using the NDK. So Java code is compiled using the SDK, and native code is compiled using the NDK, and the way to compile it is using the NDK build, which is an executable you'll have if you download the NDK. And yeah, you can do it from terminal, but I think that Eclipse has a way of compiling it now. So how is the JNI exactly working? There's something so when Java runs, you'll define a call to system.load library in the Java space, and you'll mention the name of the library that we use, and here the name of the library was hello JNI. So the way we are going to call that is system.load library and in brackets hello JNI. So that's how we invoke or load the library, and then suppose the function name was, suppose the name of the function was get next frame. You will be defining in Java public native int get next frame, and you can call this function just as any other Java function. So I can show this in an actual program. So this is an application I got from one of the AT&T developer websites, and this is a very simple application. There's a single Java file, and all it does is it has this system.load library native code, and it defines a public native int get next frame, which is the name of the function, and get next frame will be called anywhere in the code. And if you look at the C, the libnative code is here, and this is the binary, and the code for it is in the JNI folder. And if you look at this code, here's the long cryptic function name, and it does some threading, and it does some downloading work. So it's doing some data processing, and it's using JNI.h, and it's using pthread. Pthread is the C threading library, so it's able to use the regular threading of C in this JNI code. So it's a pretty simple JNI based application, and it's a good So if you look at it, they use threads and then they use free, and it's important to remember that in Java it's there is garbage collection, so we don't create threads and then we look at exiting them, because garbage collection does that for us. But we could explicitly say close the thread or close the open file, and there are some points when you need to do that even in Java space, but in C you always need to do it, and therefore it's important to make sure that we close all open files and we close all open threads and we release all the strings or yeah, and the log underscore print is just it's a system logging API, so you can, rather than, because you can't have print statements, so you can log using this. So yeah, there's certain things you need to remember when using C code. There is the Java virtual machine. It takes care of garbage collection. It takes care of protecting against buffer overruns and stack smashing. But there is no such thing in C, and the JVM cannot work on the C library that you include with your application. So therefore it's important to do more testing if we have JNI based C programs inside the application. So it's not because it's outside the sandbox. The sandbox applies to the C programs as well, and the C programs will run as the same user as the Java programs. However, just because it's inherent to the language itself, C has lesser protections compared to Java, and therefore we need to be a bit more careful. And certain other things that need to be remembered is that when we use pthreads, you need to make sure that you detach the threads, or you free the threads. So make sure you close the threads before you quit or pass the control out of the JNI. Otherwise the thread would be orphaned. And yeah, all arguments passed in JNI are local variables. You can define global variables. And also in Java space, if you have context listeners, if you have multiple threads, it's nice if your application is going to pause. So it's nice to make sure that you define your context listeners and your threads to stop inside the onPause method, so that if Android needs more memory and it puts your application in it closes your application basically, then you don't lose memory because of it. Because even though Android does do multitasking and you can run many apps, Android has a way of swapping in and swapping out applications if it's running out of memory. So that's it about native code and multi-threading. Are there any questions?